Hey everybody, it's Ripley, back again. We're in section 3.2. We're going to blow through this one pretty quickly. I'm going to give you the rules and I'm going to do just a couple of examples and then I'm going to let that fly. Tomorrow in class, I'm going to prove the quotient rule. I'm going to prove the product rule. I'm not going to prove the quotient rule until we have something called chain rule because it's a heck of a lot easier to be able to prove it with chain rule than it is to prove it with the product rule. Okay, but don't worry about that for now. All right, now what we want to be able to do is we want to be able to take the derivative of two functions f of x and g of x when we take their product. Now I'm going to give you the rule. The rule is simple. All it is it's the derivative of the first times the second as it stands plus the first as it stands times the derivative of the second. Now, for me, when I write this out, if I think of this as the derivative of u times v, I just go u prime v plus v prime u. That's how I think of it. In other words, you take the derivative of the first times second as it stands plus the derivative of the second times the first as it stands. That's really the easiest way to do it. Now, where does this come into play? We got to be real careful here because when I give you a tool, that tool may be a little tiny framing nail or it may be a gigantic sledgehammer. And this rule in the wrong hands can behave very much like a sledgehammer. Okay, so let me give you an example. If I'm trying to take the derivative of e to the x times, I don't know, 5x squared plus 4x. Okay, I'm going to take the derivative of this guy. Now, if you think about it, I think of this as being u and this as being v. So it's real simple. It's the derivative of the first term, which is just e to the x. Remember, the derivative of e to the x is itself, times the second as it stands. So I do not mess with the second at all. So times 5x squared plus 4x. All right, so that's this guy times this guy, plus the derivative of the second term, which is 10x plus 4, right? The derivative of the sum is the sum of the derivatives, so I'm starting to incorporate all of these rules at once. The derivative of 5x squared is 10x, the derivative of 4x is 4, and then I have to multiply that times the first as it stands. Now, the question that I always get asked by students is, when am I done? In other words, when have I gotten to an answer? All right? Now, at this point, we have officially taken a derivative. Okay, but the question is does that help us at all? Down the road, as we learn more and more about derivatives, we're going to realize that we need to actually use this derivative to be able to tell us things. So I do want to simplify. So we're going to call this Rip's rule. And Rip's rule in general is do at least one more step of algebra. One more step of algebra after you take the derivative. All right. Now, really, if you think about it, the calculus, remember this real scary monolithic thing that floated out there for so long in our mathematical careers, is just whoop, it's right there. It's like a drop of water in the bucket. The rest is algebra. Calculus sits over mathematics like a shell. We still have to do a whole bunch of algebra, all right? Really, algebra is the language of calculus. So if I were going to clean this up, I would notice that they both have an e to the x, so I would factor out an e to the x, and I would turn this thing into 5x squared plus 4x plus 10x plus 4, and then I would look and say, oh, duh, my spidey sense is tingling. I have two terms that I can combine there, so I could write this as e to the x times 5x squared plus 14x plus 4. And that's really done. If there's a little voice in your head at this step that says, you know what, I should combine those, then combine them. Now at this point, if you wanted to, you could distribute the e to the x through and call this e to the x 5x squared plus e to the x 14x plus e to the x times 4. But really, there's not a whole lot more simplification. Really, in general, the most factored chunk is what's best in terms of us being able to use it. Now, excuse me, I can't factor 5x squared plus 14x plus 4. It's not a factorable trinomial. So I'm just going to leave it there, right? Because 10 and 2 is 12, 4 and 5 is 9. Yeah, that's not going to work, okay? So that's it. Now, let me show you. Let me change the colors of pens so that we realize red bad. I will sometimes see students, okay, y equals 5x to the 6th, okay? And especially when you're first learning, you're like, oh, Ripley just gave me a rule. I have to use it. Well, maybe. Sometimes, sometimes not. Some students might actually see this as a product of 5 times x to the 6th, in which case, according to the product rule, I would take the derivative of the first, which is 0, times the second as it stands, x to the 6th, plus the first times the derivative of the second, which is 6x to the 5th. And the answer is 30x to the 5th. Well, yeah, but I mean, we know from experience that if I simply want to take the derivative, I just go this, 6 times 5, which is 30x, and reduce this by 1, and I'm done. In other words, don't be so beholden to these rules that you don't employ other rules that are far simpler that we learned earlier in the process, okay? All right, and I will wave my hands and scream and yell and say bad things about you if you do, okay? All right, let's do quotient rule. All right, quotient. Well, like I said, this lecture is not a very long one. I'm going to do one proof tomorrow for you guys in class so that you can actually see the proof of the product rule because it's a pretty cool proof. All right, let's do the quotient rule. All right, the quotient rule says this, and it's not as intuitive. All right, if I want to take the derivative of a quotient, so a function, two differentiable continuous functions that are forming a quotient, all right, what I do is I take the derivative of the top times the bottom as it stands, minus the top as it stands times the derivative of the bottom. So it smells sort of like the product rule, only without the pluses, but then I divide by the bottom squared. Like I said, the proof of this is far nastier if I have to try and show you the proof, but we'll do the proof of it after we have something called chain rule. All right, now the mnemonic that I use to remember this is low d high. In other words, the low as it stands times the derivative of the top. That's what d means in calculus if I say d something. Low d high minus high d low. That should be an HIGH, shouldn't it? High d low all over low squared. All right, low to high minus high to low all over low squared. That's the quotient rule. Now let's see this thing in action. You know what, we're going to need a little more. Maybe we won't. Let's look. All right, let's say that y equals 6x squared minus x to the 5th over 4 plus 5e to the x. All right, and I want the derivative of this. Okay, so take a deep breath, don't panic, and I look close. Low, as it stands, times the derivative of the top. So I'm going to do the derivative of the top first. It's a sum. I'm not afraid. I'm going to do 12x minus 5x to the 4th, right? That's the derivative of the top, times the bottom as it stands, so times 4 plus 5e to the x, minus high d low. So now I got to do high as it stands. In other words, I don't take the derivative of it, minus x to the 5th, times d low. Now what's the derivative of 4 plus 5e to the x? Well, the derivative of 4 is 0. The derivative of 5e to the x is 5e to the x because the 5 is just a constant. So it's just along for the ride, right? So this is going to be times 5e to the x, and this whole thing is over 4 plus 5e to the x squared. Now, I am not going to lie to you. Dealing with quotient rule derivatives, when I take the derivatives of quotient where they look like this, which is pretty simple, right? I mean, I think we can all agree. It's intimidating looking, but the process is very, very simple. The calculus at this point is done. We have done all that we can do with the calculus at this point. The question is how simple do we want to get it? Well, again, we want to get it as simple as we can to be able to use it. In this case, we'll just leave this as is and be happy. When I really start becoming a stickler about you not simplifying your derivatives is when you have to start using them. And that's sort of, it's a self-reinforcing skill. When you simplify these correctly, they get a lot easier to use. And when you don't, you suffer at your own hands. Okay? All right, so really, guys, that's it for section 3.2. No brainer, done and done. And that's it. So I'll see you tomorrow. I'll give you the proof of this guy right here. It's pretty fun proof. It takes about 5 minutes, no big deal. And then we'll just do a whole boatload of problems. All right? Well, have a really good day, and I'll see you tomorrow.